In this Proteus 8.10 tutorial, I will cover how to simulate and analyze some basic analog circuits. Here I have a simple non-inverting amplifier with a gain of 11. It is made up of a 741 general-purpose operational amplifier and a feedback resistor arrangement. I have calculated and set the resistor values to give me a gain of 11, but now I want to simulate and analyze it to ensure that it works correctly. Note also that the 741 requires a bipolar power supply. I have generated the negative power supply by defining the polarity as negative on the power flag. Before I can analyze this circuit, I need to provide a signal to the input and identify which lines I want to analyze. In the generators section, I will select the kind of signal I want to inject into the amplifier. There are many available and any of them will work, but the simplest will be the sine wave, so I will select that. Place and connect to the input. Right-click and enter the properties. Here I can select the amplitude, frequency and offset of the signal which will be generated. I will set the frequency to 1 kHz and the amplitude to 100 mV. The amplifier should have a gain of 11, so I will expect this to produce an output of the same frequency but with an amplitude of 1.1 volts. I will also be measuring the output voltage, so I will go to the probes menu, select a voltage probe and attach it to the output pin. From the graphing menu, select the analog analyzer and place it on the design pane by clicking once, dragging out to the size you want, and then clicking again. Click and drag the signal source onto the graph and press the spacebar to run the analysis. By default, the simulation time is set to 1 second. But this signal is 1 kHz, meaning there are 1000 cycles displayed here, and they can't be distinguished. Right-click the graph and edit the properties. Here you can set the start and end times to simulate. I will leave the start time as 0, but set the end time to 5 milliseconds. This will now display only 5 cycles, which can be distinguished. I can now drag in the probe and press the spacebar again to rerun the analysis, and the output waveform is also plotted. I can also see that the amplifier is working as expected, because the output and input signals are the same shape, but the output is 11 times larger than the input, with an amplitude of 1.1 volts. I can make the plot fill the window by double-clicking on the green bar at the top. In the full screen mode, I can left-click and hold to drag a measurement cursor. There is a small cross which indicates where the cursor intersects the plot, and the horizontal and vertical values are given in their respective units in the bottom corners. I can also run a frequency analysis by selecting the frequency analyzer from the graphing menu. Place in the same way as before by clicking and dragging out to a size and then clicking again. The frequency analyzer will inject a variable frequency signal into the input and plot the gain and phase of the amplifier output in each case. Drag both the source and the probe flags onto the left-hand side of the analyzer and press the spacebar to run the analysis. This will produce the gain plot. The plot is a flat line, meaning the gain does not change across this frequency range. The operational amplifier has a limited bandwidth, and for the 741 this is specified in the datasheet as about 1 MHz. The bandwidth stated in the datasheet assumes a unity gain, meaning a gain of 1. In reality, the amplifier bandwidth forms a product with the gain, known as its gain bandwidth product. So the gain multiplied with the bandwidth is equal to 1 MHz. Here the gain is 11, so that multiplied with the bandwidth is equal to 1 MHz. Divide 1 MHz by the gain of 11, which gives the actual bandwidth of around 100 kHz. And the plot confirms this because the gain begins to fall off sharply when the frequency rises through about 100 kHz. I can drag the probe onto the right-hand side of the frequency analyzer and rerun by pressing the spacebar. This produces the corresponding phase plot for the amplifier response. I can use the instruments to analyze the circuit while simulating in real time. Under the instruments section there are various meters, signal analyzers and decoders. I can use the AC meters to give an amplitude reading of the voltages and currents on certain lines. Depending on the size of the signals, enter the properties of each meter and set the scale as appropriate. For analog circuits such as this one, the oscilloscope can be used to monitor the signals on a given wire. Select the oscilloscope from the Instruments menu and place it on the Design pane. This is a 4-channel virtual oscilloscope, so up to 4 signals can be monitored simultaneously. I can connect channel A to the amplifier input and channel B to the amplifier output. There must be a ground flag present, as the oscilloscope uses this as a reference. Simulate the circuit using the controls in the bottom left. The AC voltmeters display the RMS amplitude as shown here. The peak amplitude of the input signal is 100 mV, and the output is 1 volt. The RMS amplitude is 70.7% of the peak amplitude as is displayed on the meters here. The oscilloscope opens as an interactive window. Each channel has an adjustable gain and offset. The time base can be adjusted. Unused channels can be switched off using these sliders. I can select which channel the oscilloscope triggers on using the selector. If you close the oscilloscope window, it will not automatically reappear when the simulation is stopped and then restarted. To get it back, go to the Debug tab and select the oscilloscope window at the bottom. If the oscilloscope window is open when the simulation is stopped, then it will automatically reappear when the simulation is restarted. You can leave the meters in place even if you are using this schematic to lay out a PCB. Under the meter properties, make sure the Exclude from PCB Layout option is checked. This can be applied to any components which you don't want to include in the PCB layout. If there are components in the schematic which you don't want to simulate, then you can go to the component properties and check the Exclude from Simulation option. This component will now be ignored when running the real-time simulation.